Hello everyone, welcome to another video. In this one we'll be discussing how you can build a language model from scratch, and with this language model how we can use it for an autocomplete, right? We're gonna understand how you can build it from scratch step by step. In our previous video we discussed how to build a character level language model from scratch, and that was also a part of our AI Engineering 101 series or playlist which we are building right here. In this one we'll be discussing how you can build a word level language model, or you can also say it as a language model, and we're gonna use that language model for autocomplete. So you can see in the diagram here, uh, we have a language model which we have built, and then we are sending some words here. So suppose if we send software, then it is completing it with software engineer, software analyst, and software developer, right? We are sending senior, and for senior it is completing it with a senior accountant, senior advisor, and so on. So these are the job roles, and I'll tell you specifically why this language model is completing this word with a role. So why it is not giving a software program or something like that, but instead of that, why it is giving software engineer, software analyst, typical job roles. I'm gonna tell you add in future, and we're gonna see why, like how we have designed this model and why it is predicting the way it is. So first let's go with the problem statements. We'll be building an autocomplete engine that, given a series of words, it can autocomplete or suggest you future prediction of words. And to build this, we'll design a language model from scratch. In the process, we'll understand word embeddings. We'll also understand how you can design your neural network architecture to build the language model. And we'll also gonna see how we can inference that trained model to autocomplete our input. Right, we'll be using a very basic neural network architecture designed to build this model. It will be a basic multi-layer perceptron with 3 hidden layers, and we're gonna use softmax for our multi-class neural network architecture. So we're gonna understand everything in detail here, and before that let's quickly understand what we are building in action. So what we are building here is that we will gonna give a word, and the language model will gonna autocomplete for it. Now, in order to build a language model, we have to test it on some data. So in order to test, we are giving it a job title data. So I have a big data set which has a lot of job titles, maybe around 70,000 of job titles, and we are expecting the language model to learn it and complete it when I inference. So basically the language model will gonna learn the data set and will understand, okay, these are the data sets and these are the words, and this is how it should complete, or this is how I should generate, right? So these are the things. And once the language model is trained and it has been decently trained on enough data, and after that when we give some word, it will gonna auto complete on the job role. So if I give software, it will gonna predict software engineer, software technician, software specialist, and something like that. So we're gonna see in action what we are doing here. So I have already explained that we'll be building a language model, and in order to build this, let's understand what data set we'll be planning to use here. So I'll be using a data set from Hugging Face. We can see it here. This is the data set which we'll be using. It's a BSTDS job titles data set. The data set, this is the Hugging Face website, so I'm picking an open data set from here. You can see the data card. It has a lot of job titles, so you can see 3rd grade teacher, 3rd mate, 4th grade teacher. A lot of these are there. It is sorted in lexicographical order or alphabetical order. That's why the numbers are first, then the alphabet, so the standard format. You can see a lot of job titles here, and if I see, there is, like, in the training data set there is 73.4k rows, meaning around 73,000 of job titles are here, and we'll be training our language model on these job titles. And once this is trained, our language model will able to understand the job titles, or basically our language model will be able to spit out more job titles, or maybe also will be able to auto complete the job titles. We'll also understand how a language model works, how word embeddings work, how word embedding works, or basically how a model learns the word embeddings and how the model produces the words at the time of the inference. So we looked around the data set which we'll be using to build this language model. Now let's quickly understand how this, once we have built the language model, how it will look like and how it will perform. So what I have done is that I have built this language model, or basically I have trained this model on Kaggle because I wanted to train it for a lot of iterations, and Kaggle allows me to use GPUs. So if you don't know, for every user, Kaggle provides some hours, I guess 32 hours or 33 hours a week of GPU usage time. You can utilize that time to train your models on the GPUs provided by Kaggle, and it will gonna fasten your training process. And it will also, like, I have seen that when I train it on my local machine or on my locally on my MacBook gets heaten up, and I probably don't like that. And the training process is also slow. So what I used to do is that I just open up Kaggle, I import my notebook from my local machine, what I have written, and then just for the training purposes, I use Kaggle. I enable the GPUs on my Kaggle notebook, and I'll use it you have to make some settings. Basically, you have to transfer all your tensors to the GPU in order to run it on GPU, and you have to also enable the GPU chips, or basically the preferences in the settings of the notebook, so that it picks up the GPU from there, and then you can run it, and you will see the training process fastens, and you'll be able to train your model faster. So I'll go through the entire process, but let's see first the model in action, and then once we are building this language model from scratch, I'll gonna show you that how you can do that in Kaggle, how you can maybe select the preferences of the GPUs, how you can move your tensors to the GPUs, how you can verify that whether your tensors have been moved to the GPUs or not, and then we're gonna train and we'll see how fast it goes. Okay, so I'll quickly show the notebook. So this is the notebook here. I'm in the middle of the notebook because I just want to show what what the end goal is, or what we are expecting as a result when we build this language model. So understand very carefully, this is the cell which we are on, this is the method, this is the inference method. So think of that, I have already trained my language model here, and I want to inference. For inference, I want to give a word. So think of it like an autocomplete. You give it some word, and it will gonna predict the words which should follow. And this is how an autocomplete looks like, right? The only thing is it happens on a doc, or when you are writing something, or when you're writing a code. When you have entered a word, it tries to predict the series of the word, and then you can maybe hit a tab or an arrow to complete that, right? This is also following the same architecture. The only thing is I'm giving in the word, and I'm predicting some inference for that. So my starting word is software, and I can see what the inference should be, right? So I can run this, and it will gonna put the samples here. So for the first case, I want 20 samples. So basically I'm asking the model that, hey, can you give me 20 predictions for the start word software. We'll also see going forward that how to how you can understand that neural network has finished predicting for a single word, because at the end of the day, language models are nothing but the autocomplete engine. They're gonna spit up more words related to it from the embeddings as soon as you give it something to start. And we're gonna see how we can understand that your language model is done predicting, so that you can move to the next data set to predict. So yeah, we're gonna cover all of this. Never mind, let's see what happens here. We're gonna get 20 predictions from the network, from the model, starting with software. So if I run this, it will gonna put the data in the samples, and I can see the samples here. So these are the samples. These are 20 samples. It starts from software technician, software manager, software engineer again, because I guess in the job title or in the data set, software engineer has been used a lot of times. Software development, software project repairer, software person, software engineer, software CCNP manager. So you can think of it as an autocomplete, and it's not very good because the model I have used is a multi-layer perceptron. I have not used the transformer architecture, or I haven't used very advanced techniques, very advanced embedding techniques to make it a lot better, but it will gonna produce some decent results. It will also produce some garbage like software VA, software cashier, doesn't make much sense. Software CCNP manager, I don't think that it makes much sense. Software person looks okay, but for that as well, I don't think. Software project repairer also doesn't make much sense, but apart from that, a lot of things make sense. Software engineer makes sense, software analyst makes sense. It is saying software engineers multiple times because it is highlighting that software engineer can be the one of the most highlighted prediction for an autocomplete, because when you type the word software, there's a huge chance that you will follow up with an engineer, and software analyst can be there, software manager, software specialist, software supervisor, software development, a lot of things can be there. Okay, so this is what we are building. You have seen this in action. Now let's gonna understand how you can build this kind of language model from scratch. Now we have seen what we are building in action. We are giving a word and we are getting some job titles, relevant job titles, like when we give software, we got software engineer, software technician, software manager, software developer, things like that. And that's what we expect our language model to do. So you can think of it as a very small language model which is trained only on job titles. So it only knows job titles. It doesn't know anything else. The only thing it knows is job title. So what you can use it for, you can use it to generate more job titles, you can use it to provide autocomplete suggestion for your word to complete it with a relevant job title. You can do things like that. Now if you will scale this language model to a bigger data set, you will be able to do much more with more compute power and with intelligent architecture decisions. Like for this I have used multi-layer perceptron, a very basic network architecture. But if you'll move on to RNNs, or if you'll move on to LSTMs, or even if you move on to the transformer architecture and you train a big corpus of data and you produce a language model, you learn them embeddings, then you can maybe do a lot more things. Okay, so now let's understand what we are doing, because we have to build this from scratch, and in order to do that we have to first prepare the data set, right? The first thing is to prepare the data set, to clean the data set, to format it in the way we want it to be fed into the neural network, and so that it can be trained, right? So this is the feature engineering part. We're gonna prepare the data set. In this we are training on the job title data set, which has around 73,400 job titles. We'll use this for our neural network to learn and later perform autocomplete. So this is what we want to do. This is a highlight of this is a part of the data set which we have already discussed earlier. Now this data set will be fed, and we're gonna split this data set into words. So you can think of it, the first data set, let's take the first example, first grade teacher, right? We're gonna split this into words. So this job title first grade teacher got split into 3 words: first, grade and teacher, and we're gonna show it like this. So when we are showing it, you will see the gray block with a dot symbol. You can think of it as a start and the stop words. So in our data set we are keeping the start and the stop words same. So why is this needed? Because we want to make, or basically we want to make the neural network understand that what are the good start words and what are the good end words. And this is important because this will gonna train the model in that way. Because you can think of it, if a teacher is followed by a lot of dots, it means that most of the job titles end with a teacher. So you can think, if person is writing a teacher, then there shouldn't be any autocomplete. Or suppose if I'm writing an engineer, or if I'm writing a manager, there shouldn't be an autocomplete ahead, because most of the job titles are ending with engineer or manager, like software development engineer, a research engineer, test engineer. You got the gist, right? Most of the job titles are ending with an engineer. So in that case, if I add a stop word, or basically a stop character after engineer, and I'll fed if these kind of examples are fed to the neural network multiple times, the word embeddings, or basically they'll gonna understand that engineer is followed by a dot, meaning a lot of job titles end with engineer. So in future, if a word engineer comes up to me, then the embeddings will guide me to predict a stop word going ahead. Similarly, a lot of words can be a starter as well, like software. A lot of job titles start with software: software engineer, software engineering manager, software development engineer, software test engineer, software architect, software designer. A lot of job titles are starting with software. So in those cases, I'll have a start character followed by a software. So if this dot is followed by a software, it means that it helps the neural network to learn that software is a good start word for a job title. Hence these stop and start words are used in the dataset. So initially you can think of the dataset to be a simple block, 3 blocks of start or stop characters, because these are the same thing. Now one thing to note is that we have already built an a character level language model. So you can think of the design is influenced from that model itself. And in that model as well, when we built the data set, we had 3 blocks of characters, or 3 characters in the context followed by a target. We are following the same design. We are keeping 3 words in the context followed by a target. So initially these 3 blocks will be start or stop characters followed by first. Then the first will gonna move to the left, and it will be a part of the context, so that the neural network can understand if there is a first, then it should be followed by a grade. This is for this specific example. Now it again moves, our data set again moves to the left. So we put more words in. So if it is dot first grade, if you have, so neural network will gonna understand if the data set or if the context is first grade, then I can follow it up with teacher, because teacher should be the target variable. Then at the end, first grade teacher, ending with a stop character. So the neural network can understand if the word is teacher, or if the context is first grade teacher, then maybe I can end it, or maybe I shouldn't suggest any autocomplete, because it should be ending, because it can basically understand that the job title is ending, right? So that's why it is very important to provide the start and the stop character. Now what we can do is that we cannot give these words directly to the neural network, because I have explained earlier while designing a character level language model that neural network does not understand natural language like English, and they'll not make much sense of this data, or basically they'll gonna train poorly. So what they understand is numbers, and for that we're gonna convert these words into IDs, right? And in order to do that, we're gonna build our dictionary, or we're gonna build our vocabulary, where we will have all the words, all the distinct words which is present in the data set of job titles. We're gonna put it in the dictionary, and we're gonna map those words to the ID. So you can think of first is mapped to one ID, grade is mapped to another ID, teacher is mapped to another ID. So you can think of it, these words now will be represented there by their unique IDs. And we'll also have a reverse mapping, so that when we'll get the inference from the neural network, we'll get those IDs and we can map back to the word, so that we can generate relevant job titles, right? So we can convert these words into the index mapping, and this will look like this. So you can think of ID as a map which can take the word as a key, and it can produce the ID for that word. So you can think of it as, the design is simple. I have just replaced the words by their IDs. ID first, ID of grade, ID of teacher, ID of grade, ID of first. So all of these are like this, and we have the ID of the start or stop character. Ideally it should have been here as well. In all these cases it should have been ID of first. So maybe I can fill it up. It got missed. So yeah, this looks better. So all of these have IDs now, ID of start and stop character followed by the ID of the words. And this is how our prepared data set will look like. Now again, this is not it. We are not sending this data set directly to our neural network. We're gonna convert, or basically we're gonna map these IDs to their vector embeddings, because if I give a single number, the neural network will not gonna learn much about the word. So we're gonna give a series of words, or basically we're gonna give a series of numbers. So if this single word is represented by one ID or a number, we're not gonna give that single number to the neural network. Instead of that, we're gonna give a series of numbers. And what should be the size of the series of the number, that is decided by the dimension size of your embedding. So if I say that my embedding has a size of 5, basically if I say that I'll be using a 5-dimensional vector embedding, it means that every word will be represented by 5 vector embeddings, or basically by 5 numbers in a high dimensional space, right? So that's what we're gonna give to the neural network, and then neural network will train and we're gonna learn those embeddings the way it want, so that it can inference with some relevant information or relevant job titles, right? So this is what we're gonna do. So this lecture is divided into 3 parts. This is the first part, which is the feature engineering. Second is understanding the neural network architecture and training the neural network model. The third part is the inference, where we're gonna use the trained language model or the neural network to give us some or predict some relevant job titles, perform some autocomplete, and we're gonna understand how it works. So we have discussed about feature engineering. Now let's see how we can build this from scratch. So I'm gonna go back to my Kaggle notebook, and this time I'll gonna walk you through from the start so you can understand step by step what we are doing here. So this is the notebook. I call it job title embedding learning, because what we are doing is that we are building an embedding, or we are uh, making the neural network learn the embeddings which comprises of the words used in the job title dataset, right? So the first thing to do is that you should import your libraries, and you can see that this is being done in on Kaggle. So I am not installing any library on my local machine. Whatever we are doing like online on the notebook, and these libraries are already available, so you don't have to install anything. You can just import that. It is already there in the Kaggle, so I can import all of these, and it is done now. The important thing here is that we will want to use, or will basically want to use GPUs to train our neural network, because if you will use CPU, you'll see that the speed of on which the network learns, it gets slowed down a lot. And if you want to train it for a huge number of iterations, and if you want to see some real performance improvements, then it is always helpful to use a GPU, and Kaggle provides it for us. So if you'll go to the settings in your notebook, you'll be able to see the accelerator, and if you click on accelerator, you will see the GPUs available. Currently I'm using GPU T4 for this, and if I'll enable it, if I'll select it, I'll have this in the sessions. I'll have the GPU session as well. It will gonna tell me how much utilization of GPU is happening when I'm running a cell. Currently it is empty because I'm not running any cell, and hence no utilization, but you'll see this. And if you will see that you have enabled GPUs, but still the utilization of CPU is higher and GPU is still blank, uh, it is a high time to understand that there is something wrong in the implementation, or I guess a lot of my model is still running on the CPU, and you should debug it. In order to debug, basically in order to understand what is happening here, you have to first be sure that your device, or basically your device, has the GPU enabled or not. Basically once you have enabled it from the settings, you can do that by this code. You can pick the device, and you can see whether the CUDA is available. It shows whether the GPU is available or not. And when I run it, and when I open the device, or basically when I print the device, you can see device type equal to CUDA. It means that the GPU is available on my notebook to be used. Now the important thing is, once you have the device in hand, you have basically the device which is CUDA basically in hand. Now what you can do is that you have to move the tensors to the device, right? And what you are doing is that you are moving your tensors from CPU to the GPU, so that when you run it, you can utilize your GPUs, and you can train your model on the GPUs. So you'll see that in future, whenever I am introducing a tensor, with defining the tensor, I am also moving it to the CUDA device, or basically to my GPU, so that I can train it on the GPU. And once I am done, and well, you'll see when I'm training, you'll see the GPU utilization will be higher than the CPU. And for all these normal processing, you'll see the CPU utilization only, because here we are not using GPUs. It is the standard CPU processes which will be happening here. So what I can do first is that I have to import the dataset, and since I mentioned earlier that I am importing the dataset from the Hugging Face library, and it provides a very seamless way to import the dataset. You just have to import the load dataset from their datasets library, and then you can give the name of the dataset, the open dataset which they have already hosted. You can provide the name here, and it will gonna load the dataset for you, and it will gonna load the dataset in this data frame. So I can run this, and it will gonna get loaded in a few seconds, and I guess this is done. And I can visualize what I have loaded here, so I can just run this. Okay, I think this is taking time. Okay, let me print out the data set here. Ah, Okay, I have the data set. Okay, cool. That makes sense. I have the data set. I was just appending the data set into the job title. So you can see if I print the data set here, the data set has the number of rows in the data set is 73,380, and this is around 73.4k, which we saw earlier in the data set, in the data card of the data set on the Hugging Face. The features which I have is the ID and the name, and we are only we only need names. Basically we only need the name of the job titles. So I'll gonna pick all the names, or basically all the job titles, and I'll gonna store this in my job titles array. Let me do that very quickly. Now it's done. Now I can show you the first 10 job titles which I have. So these are the first 10 job titles. We saw that in the data card as well. First grade teacher, first pressman on by press. These are the data sets which we have. I can also see how many job titles I have imported from the dataset, and it is the same, the number of features or the number of rows which the data card had. It is 73,380 job titles we have imported. Now the important thing which we should do is that we need to build a dictionary so that we can make our word index mapping or word ID mapping. So the first thing we'll do is that we're gonna build our dictionary. In order to do that, let's understand how the job titles looks like. So you're seeing that some job titles are long, some job titles are smaller. Generally we have seen the job titles in the range of 2 to 3 words: software engineer, software development engineer, software tester, programming analyst, research engineer. Like 70 to 80% of the job titles does not exceed the word size of 2. It comprises of 2 words only, but in a lot of different cases there are more than 2 job titles as well, like software development engineer, a web solutions engineer. These have 3 words in the job title. The job title can go longer as well, so it is always good to understand how the distribution of the words, or how the features looks like in your data set. So one of the feature is the number of words in a job title. We're gonna visualize that. In order to visualize that, we're gonna build our word length map. What it has is that it will gonna, for every job title, we're gonna split, or we're gonna count the number of words, and we're gonna store that as a key so that we can see at the end how many job titles are there in my data set having 2 words, how many job titles are there with 3 words, and so on and so forth. This is the code for it. It's fairly simple, not much happening here. We are just putting it by the number of word keys, and we are incrementing it whenever we found more of these. I can see the length of the word length map. It has 10 indexes, meaning it might be from 1 to 10. So how many job titles with 1 word, how many job titles with 2 words, how many job titles with 7 words, so forth and so on. I can plot this and I can show you. So I'm gonna do a bar plot with the keys and the values to showcase how this distribution looks like. So as we have thought, uh, the number of job titles with 2 words and 3 words is the majority in the dataset, and with there are some job titles with 4 words as well, and some job titles with 5, and a very few job title with 6 word. Some job titles, a very few job titles is also there with a single word. So what we are dealing with here, 70 to 80% or 90% of the job titles in our data set has 2 to 3 words, and that is all right. I think this is an okay data set to start working with. I don't think we need to perform any feature cleaning, because there is no empty words, or there is no empty job titles, or there is no job title with a huge like 100 200 words. So this is what we expected, and it is okay. We can use this without any feature cleaning or any data set modification. We can use that as it is. So let's build the dictionary. In order to build the dictionary, we have to understand first dictionary is. We have built the character level language model in our previous episode in this AI engineering series. What we did is that in order to build the vocabulary there, we picked all the distinct characters present in the data set. Now that was the character level language model. Here we are building the word level language model. So instead of picking the characters, we'll pick distinct words. So what we're gonna do is that we're gonna go to the job titles. We're gonna split the job titles into words, and we're gonna store those distinct words in a dictionary. So if software is coming up 10 11 times, it will only be stored once because it's a set. So what we are doing is that we are going through the job titles, we are splitting each and every job title into word, and we are storing a word into a set, so that uniqueness is maintained, and then we are converting it into back into the list. So the list will have, it will be dictionary, and it will always have unique words, right? So we can run this, and it is done actually, and we can see what is the length of the dictionary we have. So our dictionary has 12,157 words. So we had 73,400, yeah, 73,400 job titles, and from those job titles we have built our dictionary with 12,157 unique words. So this is our dictionary. I have print first 10 words of the dictionary. This is underliner, anesthetist, body aid, Zanjero trap, stockbroker, carbonating, stuff like that. So these are picked from the job titles. So it looks like the job title only. Now we have built the dictionary. We discussed that we will build the dictionary, and after that the second step is to convert the word into IDs, or basically to build the index to word and the word to index mappings. And this is very important. We did the same thing in our character level language model as well. The only difference is that here we are doing this with words, what we did earlier with characters. The stop word is the dot, which I show earlier in the when we are going through the presentation. So the stop word is this. We're gonna use it at every step when we are building the data set. The index for the stop word is 12157. There is a reason I have used this, because the length of the dictionary is 12,157, and if you index those words starting from 0, it will gonna end at 12156, and that's why the next index, that is 12157, can be reserved for our stop and the start word, right? The stop and the start word are same, so I'm using stop word here for the ease, right? And the stop word index will be the index of that stop word. Now the second thing is we have to build the index. So first we are building the index to word mapping. What we are doing is that we are enumerating the dictionary, and we are picking the index and word, and simply we are building the map. After the map is built, obviously the dictionary doesn't hold the stop word. It is the word which we have introduced ourselves. So we have to explicitly add that as well in our mapping. So what I have done is that I have added the stop word index with the stop word. So now along with all the indexes to the word mapping, our map also holds the stop word index mapped to the stop word. Now I can reverse iterate that mapping to get the word to index mapping, and that's what I have done in this code snippet. The good thing with Python is that you can do a lot of this complex logic in just 1 or 2 lines of code, and like maybe in 5 lines of code I have done all of this. I can run this, and yeah, the index to word and the word to index mapping is built. Now this looks vague. We have to build the data set as well. Since we have the mapping, I can show you the mapping can be looks like this. So when I can maybe index to word, I can index, okay, it is indexed to word, so I have to feed in index. So if I say index 1 2 3, it gives me hydrate. So the word hydrate is indexed with 1 2 3. I can do a reverse mapping as well to just understand how it works. So I can do word to end, and in the word to end I have to pass software, or let's pass hydrate, and let's see what we get. We should get the specific index as well, which we used earlier. So we got 1 2 3, which we used earlier. I can use software, and I can see the index. So software is assigned with an index of 11,158. So all of these words in our job titles we built using dictionary now is into the word to index and the index to word mapping. Now what I can do is that I can build the data set. As I explained in the presentation, the data when I'm building the data set, I'm using a context, and the size of the context, or basically the block size, is 3. So at once each data set will have 3 words followed by the target. So the neural network will see 3 consecutive words followed by the target, so that they can learn. So they can see dot software engineer manager, where manager is the target, and dot software engineer are the 3 words in the context. So in order to build that, I'll use I have iterated through all the job titles. This is the method which is doing this for us. I have written it from scratch. So the job titles which we imported, I am iterating through the job title, and for every job title I am splitting them into the words. Now the first context is the stop word. So initially my context is filled with 3 consecutive stop words. What I'm gonna do is that I'm gonna move my data set or move my words step by step into the context, and I'm gonna push from the left. So you can think of it as a deck where we are pushing it from the left and I am pushing it from the right. So all the words along with the stop word goes into the data set, into the context. So the first context is the context. Actually the first data set is the context and the target is the next word. After that I pushed the left word in the context using this, and I pushed the right word into the context. So what it has is, I showed the example earlier. So the left side will be cropped off and the right side will be added here. So I can show you what would have. So suppose you have dot 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 target to maybe software, then at the end you will have dot, if this, once this is done, you will have dot dot software followed by the next word. Maybe it might be the engineer, it might be engineer as well. It will do something like that. The only difference is instead of word it will have their indexes. So at every step we're gonna push our data set in to the context, and there will be one target to the right side, because this is what it is doing here. And if I repeat that, I'll get a lot of these 3 sized blocks with their target. And once this is done, once we have appended all the data set, I can convert this into the tensor so that I can give it to the neural network. So we are using PyTorch as it is an open source framework for building machine learning models. So we are building the neural network on PyTorch, and it operates on tensors. So we have to convert everything into tensor, every data structure. So the list which we have used, I'll convert this into the tensor, and I can return these data set which I have used. So I can quickly run this, and it ran. The important thing to say is that whenever I am defining tensor, I am also adding this dot to device. Now I explained earlier that we need to move our tensor from CPU to GPU, so that when we train our model, it gets trained on GPU, not on CPU, and it gets trained faster. That's why we already defined the device, which was CUDA, that is the GPU. I am moving my tensor. Once I have defined my tensor, I am moving them to the GPUs, right? And this is an important thing to do if you want to train your model on the GPUs. And then after that, I'll gonna return the data set. I've already defined this, so I can run this. It will take maybe a couple of seconds. Okay, it is done. The block size is 3, so it will have a lot of block sizes. I can visualize this data set. Now in order to visualize, I just have to perform a reverse index mapping. So I can take this data set that is done from the word to index mapping. So whatever word we have is converted into the index of 3 block sizes followed by a target word. Now if I will pass back it to index to word mapping, so I can get the index and I convert back to the word. This is how our data set will look like. Now this is what I commented up earlier as well. This is how it will look like. Initially the first 3 blocks are the dots, that is the start characters followed by first. Then we're gonna push our data set, or basically pushed our words to the left, and we're gonna pop the left side of the context window out. So this is a context window. We are pushing our data set from here and we're pulling it, or we are popping it from there. So we popped one of the stop characters and we pushed the first word here. Then along with first we pushed grade here, and now the target is teacher. Now we pushed first grade and teacher, and the target is the stop word. Now like this I can do that for the entire job titles, and I'll get the data set something like this. Now this is only the first, I guess, first 20 values in our data set. The length of the data set is much more than that. I can visualize this when I see the shape. So if I print the shape, I can see I have 269,180 data sets, and this 3 represents your context window. We had a block size of 3, that is why the context window is 3. and the target is also 269,180, obviously because we are appending into x and y at the same time. And this has no dimension because it only has a single word, that is the target word, right? So 269,180 cross 3, that is the block size. So we have a lot, enough of data set to train. 269,000 is a big number, and obviously in order to train this big number, or in order to feed this big number, we need to like have that architecture support. So that's why we are using GPUs here, and going forward you'll see like how fast and we can train this. So this was it for feature engineering. In the next part we're gonna see how you can give this data set which we have prepared to the model, and you can see how the model gets trained, and then we can see the inference part. So we understood the feature engineering. Now let's move on to the machine learning part, where we're gonna discuss what the architecture of the neural network should be and how we can train the neural network, and then we can see how we can inference that. Okay, let's quickly move on to this. Building the neural network architecture is the second part. So we'll be using a 3-layered neural network, which has a fully connected layer followed by a batch norm and then followed by a tanh activation function, right? So if you have gone through my previous episode, one of the previous episodes in the series that was on building a character level language model from scratch, there as well we used a similar architecture, where every fully connected layer was followed by a batch norm layer and a tanh activation function, and I explained there as well what these topics are. I can quickly show you here as well what these are. So this is batch norm in PyTorch. What it does is that it normalizes your features, or basically your weights and the parameters, to make them behave, to make them in a standard or a general range. What it does, or how it does, is that it subtracts the mean value from the numbers and divide the value by their variance to make them in a certain range, right? And tanh is one of the activation functions. There is a lot more other activation functions which you can use in while you are building the architecture of your neural network. You can use ReLU activation function, you can use sigmoid, a lot more are there. Tanh is also one of the activation function which squashes your values within the range of -1 to 1. So it is like it tries to squash the numbers. If any number is going way above or way out, it tries to squash it to a decent general range within -1 to 1 probably. This is the mathematical function where if you want to uh, apply an activation function on a number, you put that number, and this is how these numbers are treated. So we use exponentiation function to, and we raise it to the power of x. X is the input to the activation function, and this is how the graphs looks like. So you can see the most of the numbers are in the range of -1 to 1 and within a sweet spot, so that we can like use them for an effective learning when we are training the neural network, right? So I can minimize it back, and this is how the flow will look like. The first thing we'll do is that we're gonna remove the noise and build the word index mapping. So we saw in our job title dataset there was not much noise, so we didn't do that, but we built the word index mapping and we also built the reverse mapping. After that, with the word index mapping, we build the dataset. I show it earlier as well. We built the dataset where the context window was of 3 words, so 3 words followed by a target word. After that, you can perform the train test split. I guess this is not much required for our current scenario, because we are building a language model and we want it to generate more relevant words, so that's why we're gonna use entire of our training set to train the language model. The important thing comes up in the second part, that is the machine learning, where we convert our dataset into the embeddings, because I mentioned earlier that we are not passing the index directly, we are converting them into the embeddings, and then we'll pass that. Once it has been converted into the embeddings, we'll pass it to the model, or basically first we're going to set up the model architecture and then we'll pass it to the model for training. We'll spend some time in training the model, and after that we're gonna inference, and while inferencing we can see how it auto completes or how it can generate more random job titles. This is the architecture of our neural network. You can see, I can zoom it up a bit. Okay, this is good. So you can see this fully connected layer which has some neurons, followed by a Baston layer, and then followed by a tanh activation. These are the two layers, and after that the last layer, the third layer, is a layer of multi-class classifiers. So what we are doing is, in the multi-class classifiers, the neurons is equivalent to the number of words in the dictionary. So we had around 12,000 words in the dictionary. So this the last output layer, the number of neurons present in this layer is equivalent to those words, because every neuron, we think of it as the probability of a particular word. So you can think of this neuron as giving you the probability of word 1 being the prediction, this neuron giving you the probability of word 2 being the prediction, and we are doing the similar thing for all the words present in the dictionary, so that every time a neural network predicts, we can get a probability distribution of all the words in the vocab, and we can pick the efficient words on the basis of this probability distribution. So we can see that once a neural network will predict, it will gonna give higher probability scores to the more relevant words, and will be able to sample those important words so that we can make some relevant text generation, right? And that is why we are using the multi-class classifier architecture at the end as an output layer, right? So these are the number of words in the dictionary. I have visualized it. You can also visualize it by this. I can zoom it out so that we can see this. So while training the neural network, the multi-class classifier, this will have the words present in the dictionary. The output of this multi-class classifier will be called as logits, and we're gonna convert this into the probability distribution so that we can sample from it. Now what you can see is that uh, the target word is engineer, and the target was engineer. So what we can do is that among this word, so this will have all the words in the dictionary. Suppose W3 was engineer, and once we get the output from this multi-class classifier, every neuron will gonna have some output, so every word will have some outputs. We can think of that as the probability scores assigned to those words, and we can tell the neural network that, hey, for this particular output you have generated, the target word should be engineer, so you should focus on strengthening the weights of W3 so that we can predict engineer for this case, right? And in this way we're gonna train the neural network repeatedly on multiple data sets. Like I guess we had around 200k data sets while doing feature engineering, so we can train on all of these situations, and we can train the model accordingly to let so that they can modify their weights through back propagation. So we are telling the network to learn the target word for a series of input words given to the model. And how we are doing it? We are doing it through cross entropy loss. So cross entropy loss is a defined function in PyTorch. What it takes is, it takes the logits along with the target word. So all this entire output, this is logits. You can give all this output from the neural network to the cross entropy loss along with the target word, that is engineer, and it will gonna compute the loss. So the loss will be defined by the values of this multi-class classifier. So suppose if W3, that is the output for engineer, if it has a higher value, then the loss will be low. If W3, the output for engineer, has a lower value, while other words, the value of other words are high, then the loss will be high, telling that, hey, you should have predicted engineer, but you are predicting other words, and that is not the case. That's why I'm gonna increase the loss, so that you can learn that you have to predict engineer. Okay, this is for one scenario. You can once this is repeated for multiple other scenarios, you'll get a decent language model. Okay, I can see what cross entropy loss is. Okay, here is the documentation. So yeah, cross entropy loss, it is useful when training a classification problem with C classes. Here as well we are doing multi-class classifier where each word is treated as a separate class if provided the optional argument weight should be a 1D tensor assigning the weights to its classes. So the input is expected to contain the unnormalized logits. This is the unnormalized logits we are getting because we are not converting these logits into their probability distribution by passing it to the softmax. We are just giving the logits directly to the cross entropy, and that's why it says the unnormalized logits which do not need to be positive or sum to 1, that is the probability distribution, because once you convert them into the probability distribution the sum of all these values should come to 1. That's the standard law of probability. The sum of all the probability scores should be 1, right? This should be the input to the tensor along with the target, right? And then it will gonna give you the loss. Okay, I hope this makes sense, and there's a lot of details. You can read it out and you can understand what it does, and then we can calculate the cross entropy. The criterion computes the cross entropy loss between the input logits and the target, and that's what we are doing here. We are giving the logits and the target, and we are expecting it to compute the cross entropy loss, and this is how it does. These are some of the examples where there is some input and the target, and we are giving the input and the target to the cross entropy loss to calculate the loss, and then you can back propagate to make your network learn on the loss which the model has, the cross entropy loss has returned. Okay, so this was for the presentation part. Now we'll move on back to our Kaggle notebook, and we'll pick from the feature engineering to understand how to continue the machine learning, how we can build the neural network architecture, whatever we have seen here, and how we can train it. So we are back at our Kaggle notebook, and we are picking up from where we left earlier. So what we did earlier is that we did all the feature engineering, and at the end we visualized our dataset to understand how the dataset looks like. We also looked at the shape. We have around 269,000 datasets on which we're gonna train our language model. Before training the model, we have to see how to build one. So we discussed the architecture in the presentation. Let's practically build it from scratch. So the block size is 3, meaning every dataset has a series of 3 words followed by a target. Embedding dimension here is 5. I explained the embedding dimension earlier in this lecture as well. It is basically the number of vectors or number of integers we'll use to represent a single word in a high dimension space. So when I say embedding dimension is 5, I'll be using 5 dimension embedding vectors where every word will be represented in a 5-dimensional space using 5 vectors in different in a 5-dimensional higher dimensional space, in a 5-dimensional space, and this will help the network to learn. Okay, the dictionary size is the length of the dictionary plus 1. 1 is here because we are adding start and the stop character to the dictionary, and since the start stop characters are the same, we are adding 1 to the dictionary of the words which we have prepared. Now we are building our embedding. Initially, this embedding is unlearned, so we are initializing it with some random numbers, and once we train, eventually this embedding will make more sense, because once the network will learn, it will gonna modify these embeddings so that we can generate some meaningful samples. Okay, so initially we are initializing it with some random variables. The shape of the embedding is the dictionary size and the embedding dimension, because the embedding should be able to represent each and every word in the dictionary. That is why it is of the size of the dictionary, so that for every word we can index into the embedding and we can get the embedding of the dictionary. The embedding dimension is 5 because for every word we have a 5-dimension embedding, meaning when you will try to get the embedding of a certain word, you will get an array of 5 words because the dimension is 5, which will represent that word in a higher dimension space. That is for the embedding. Now interesting thing again is we are moving this torch to GPU, because I explained earlier that we want to run this in GPU, and every time when we will initialize a torch or basically a tensor, we're gonna move those tensors to the GPU so that we can train our model on the GPU. So I move this using the two device, and I can run this and we can see the shape. The shape is 12,158 with 5, that is the dimension of the embedding. 12158 is the size of the dictionary plus 1, because the size of dictionary was 12157. And then this is the model architecture. So the model architecture is similar the way we explained in the presentation. We have a sequential series of 3 layers. Every layer has a fully connected linear layer followed by a batch norm and a tanh activation function. At the end, the third layer is the multi-class classifier layer, and that is why the output neuron, the number of neurons in this layer, is equivalent to the dictionary size, because we want to consider it will gonna classify it into all the words present in the dictionary, and we want to capture each and every word as an output of this neural network, of this language model. That's why the output is the dictionary size. We want to get each and every words here, and this is how the architecture looks like. You can tune with the block size and the hidden layer. For this, I have kept the size of the hidden layer to be 100. Basically, the number of neurons in the hidden layer will be 100, followed by the last layer where the number of neurons will be equivalent to the number of words in the dictionary size. So I can define this model now. Now it's stored in the model. Now important thing is, once you have built this model along with the tensors, you also have to move this model to the GPU from CPU. So I'll do the similar thing. I'll gonna move this to the device, the CUDA device which we have initialized earlier. So I can print it, and the first thing is the parameters of the model. It shows you what you have defined in the model. We have 3 layers, every layer followed by a batch norm and a tanh. The last layer is the output layer, which has the number of features which is equivalent to the number of words in the dictionary, and the hidden layers have a neuron of size, or basically the layer of the size is 100, meaning there are 100 neurons in the hidden layer, right? And this is the model. We have moved this model to GPU. Now I can train this model. So for training, I show earlier that the data set, the shape of the data set has 269,000 rows, right? And even though you are using GPUs, there is no way you can give this entire data set to the GPU and you can expect the model to be trained. It will take a lot of time. It might exceed the size of the memory space as well, because there is a I guess there is a limit on the memory and the GPU utilization which we can do on a single notebook instance. So what we'll do, it's a very standard procedure. We're gonna batch our training. Basically, we're gonna train the network in batches. So we're not gonna give the entire data set at once. We're gonna give batches of the data set. So we're gonna pick random batches from this data set, and we're gonna give it to the network for training during every iterations. So for here, I have decided the batch size to be 512. That's a decent batch size. So at every iteration, you can expect 512 random data set picked from the huge data set which we have, the size of 269K. The learning rate is 0.1. I want it to learn faster, and since there is a lot of data set here and we have a smaller batch size, that's why I have a little bit higher learning rate of 0.1. Initially, I am training it for 50,000 iterations. I can increase it to 100,000 iterations, and while training, I am storing the losses so that I can show you a decent loss plot, and you can see how the losses went from the start to the end during the iterations. Now I can train the model. I have the data set X and Y. X will have the context and Y will have the target word so that the model can learn. In every iteration, I am first picking the random numbers. So for that, I am initializing a random array of indexes, which is in the batch size. So what this line does is that it says that give me a random number from 0 to x dot shape of 0. X dot shape of 0 is nothing but the length of the data set. So from the length of the data set, give me 32 random indexes so that I can create a batch. This will give you the random indexes, and you can index your data set to make the batch. Now this is how Python simplifies it. You can just pass the array of indexes, and you can index your data sets here. So this huge data set will be converted into the batches, and then you can work with the batches. Now the first thing we are doing is that we are converting those batches into the embeddings. So what I do is that I indexed the embedding, meaning uh, the initially what we have is that we have a data set of 3 indexes along with the target variable. Now every index will be indexed from the embedding space, and will that certain index will be sparsed to 5 values. So uh, if initially my index was 1 1 1 followed by 100, so suppose these were the word indexes, maybe 1 2 3 followed by 100, then what will happen is that once I execute this statement, I'm gonna index from the embedding space, and I'll ask that, hey, can you give me the embedding vector space for 1, and it will gonna give me a series of 5 numbers, right? Because the dimension of my embedding was 5. Again, I'll say that, hey, can you give me the embedding vector for index 2? It will gonna again give me some other 5 number series. Okay, and I can do the same thing again, and I can ask for number 3, and it will gonna give me the embedding of 3. Now initially, if I can remove the target variable for once, initially the shape of this, you can see this is 3, right? Or you can think of it as 1 cross 3, or since we have um, batches, we have 512 of these data set, you can think of it as 512 cross 3. This should be the shape, but once we have this, it will gonna convert into three-dimensional three-dimensional matrix, that is 512 cross 5 cross 3, because now every number is represented by 5 uh, 5 vector embeddings. So what you can get is 512 5 cross 3. Now it's our duty to denormalize, or basically to reduce this into a two-dimensional vector. So what I can do is that I can make it a 512 cross 15, because I can squash these two dimensions, and I can make it 512 cross 15 matrix, which I can give it to the neural network. So now this can be easily done in PyTorch. If you are using PyTorch, and if you have done a lot of machine learning, you should be very handy with these kind of operations, and this can be done by the view operation. So what you can do is that you can specify the first dimension, but for the second and third dimension, I'm specifying only the second dimension, which is the multiplication of the second and the third dimension. So the second dimension was the embedding dimension, that is 5, and the block size was the third dimension, that is 3. I can multiply it, and I can make it 5 cross 3, that is 15, which will result into batch size cross 15. Now this is what it is. Embedding x dot shape 0 is the length of the embedding, right? X embedding. Now this is equivalent to the number of batches, that is 512, which we have here as well. Now once we have this, we can give it to the model, we can perform a forward pass, and we'll get some logits. We explained that in the presentation. The logits are returned from the multi-class classifier output layer. Now these logits shows for every word what the model has predicted, and we are calling them logits. I can pass these logits along with the target to the cross entropy loss. Now we explained cross entropy. I explained cross entropy loss earlier. I can pass. We show that the cross entropy loss takes the logits and the target as an input. So I pass the logits and the target. The target is stored in the Y, all the target words. Now you can see that we are parallelizing a lot of things. Instead of going one dataset at a time, we are dealing with a batch of datasets. So this logits will be the output of neural network for those batch dataset, and for those batch dataset we have the target word outputs as well, basically the embeddings of the target words. And we can not the embeddings of the target words, only the index of the target word, and we can give this target to the logits so that we can understand what was the loss here. Okay, now this is what we want to do. And once this is done, once we get a loss, depending upon whatever loss was returned by the cross entropy, I can train my model, or basically I can back propagate to update the parameters. And once I back propagate, my network will learn it. This is one step of learning, and then I can uh, whatever gradients have been provided by the model, or basically whatever gradient has been calculated at this step of learning, we can move one step toward this gradient multiplied by the learning rate. So learning rate basically enhances your learning process by multiplying your gradient. The step you are taking in the direction of the gradient, the learning rate enhances that step by multiplying your gradient with it. So we are like going one step to the to minimize that loss, and this is how it is done. This is standard ML procedure, and we are at every iteration we are printing the loss. And since we are going with 100,000 iteration, if I print the loss at every step, it will gonna clutter my notebook. So what I'm doing is at every 1000th step I am printing the loss, and I am adding that loss to the losses array. So this is what we are going to do. We initialized the losses array here so that I can visualize the loss. So this is the entire training procedure will look like. I can run this, and this is now defined. Now we have defined the trained model. I have not executed it. I'll execute in the next step. So here we are executing, we are giving the X and the Y data set to the trained model, and I can run this, and you'll see the iterations are popping. First iteration we had a loss of 9.9, then we reduced it to 6.621, and this will go on for 100,000 iteration. It will take some time, maybe 3 to 4 minutes, but once this is done, we can see a decent loss here, and then our model will also be able to predict. So now we are done with the training, and we have trained the model for 100,000 iterations. I can scroll down and I can show the loss, how it looks like. So at the end we have a loss of 4.63, around that. We started with a huge value of 9.92, and you'll see the same thing when I'll visualize the losses array. You can see the curve here. So this is how the curve looks like. We started with a value of something 9.9, and then we reduced it to a very low value of around 4.5 and 4.6. So this is a good training actually. Now one important thing to note is that while training this model, you see a lot of curve, lot of up and down, lot of hills and cliffs, lot of ups and downs here. The reason is you are training on batches, and since there is a huge corpus of dataset, there can be a chance that the batch you picked and the batches you picked next, they were completely new, and that is why, or they were not trained that well, and that is why there is so much of ups and downs, because some batches were not trained enough, some batches were trained enough. That is why some produced decent loss, some produced very high loss, and that is why this is very normal. This is a standard thing which happens when you train, when you perform batch training on a huge data set. The loss curves, in general the loss goes down, but during the path of going down you can see a lot of ups and downs because you're training in batches here, and that's what we can see. After that we can inference that, because now we have the model ready, we have the trained model ready. For inferencing, I am starting with some words, and the sample count shows how many samples you want to generate from the model. The start word is the word which we are keeping as a starter. So this is the start word which we can give to the as a context, and we can feed the context to the model, and we can tell them that, hey, this is the context, what do you think the next words should be? And we can use this method to perform autocomplete as well by changing the start word to the word which I like. So I can give my word and I can let the model autocomplete. I can also give the start stop character, the special character word which we had, as the start word to the inference, and I can let the model generate some random job titles for us. And how it does is that it trains, and it is making sure that the number of the job title which it is predicting, it is not going more than 5 words, and if it is going more than 5 words, we are ending at that point and we are predicting the next sample. So this is how we are going with next sample. One more stopping point here is once the model predict the stop characters, or when a model says that, hey, after that I think there should be a stop character as a prediction, it should be a sign that the model is saying that, okay, this job title prediction ends here and you can start with another prediction. Now this happens uh, when the words like manager, engineer, these kind of words come up, where in the training corpus these words were followed by the stop characters, because these words usually end the job title: software engineer, software development engineer, test engineer, research engineer. Lot of job titles were there ending with engineer. That's why we for these words they were followed by the stop character, and that's why it is very likely that if your model is trained well, it will gonna generate the stop character after these words, so that you can end with a valid job title which can still make sense, right? So there are two ways we stop. First is if the job title, the length of the job title is more than 5 words, we stop. If the model predicted the stop word, we stop, and then after stopping we put the predicted job title into the samples, and once we are done with the sample count, once we have produced the number of sample counts which we are asking the model to do, we can return this sample. So this is what the inference look like. I can define this inference, and after that we can inference on multiple things and we can see this in action. But before inferencing, I would like us to spend more time on embeddings, because at the end, using this network we are learning the embeddings, or basically we are training the embedding vectors as well, so that they can make sense. So I'll go back to the presentation now, and we were here for training the neural network. Once we trained, we can visualize the word embeddings, because we have trained for a lot of iterations, and since we have trained for a lot of iterations, the word embeddings will make sense. And if I want to visualize the word embeddings, this is one way you can visualize it. Currently we have a word embedding which is distributed in 5-dimensional hyperspace, or 5-dimensional space, and there is no way to visualize a 5-dimensional space, obviously. So we can visualize that in a 2-dimensional space, and this is how you can visualize it. So suppose there is a word software, and if you will see the training corpus of job titles, the word software in a job title is likely to followed by software engineer, software designer, software developer, software tester, software technician, and that is why your word embedding, it will be closer, or you can think of this the word embedding of software to be closer to these words and farther away from more unrelated words like teacher, advocate, surgeon, artist, carpenter, because there is likely no job title with a software teacher. It can be, but generally these are like computer science teacher, something like that. But software teacher is where there is a very low chance of having that job title. Software surgeon, not at all. Software artist, I'm not sure. Software carpenter, software advocate, these are like, these job title doesn't make sense, and that is why these words in the embedding hyperspace, these words are farther away from the words which is likely to be followed by software, or which is likely related to the software job title. And this is one way you can visualize the embedding. Now now we have understood what embeddings are and how you can visualize this, we can use this understanding to do a lot of things with the network. Now what we can experiment is how the network can perform autocomplete, how word which usually ends a job title is not auto completed. So if I give the words which ends a job title and I'll ask my neural network to predict, the model will probably most of the time will give you a stop character as a prediction, saying that, hey, stop at that point, because this looks like the end of the job title. How different words are being auto completed differently, I can give different words and I can see how these words are being auto completed, and then we can also generate some random job titles from the network. Now these are the things which we're gonna do and we're gonna see how the trained model behaves, or basically inference or predict for multiple different scenarios. Okay, so I am back at our notebook. This was the inference method which we went through, and I have defined this as well. So now it's time for inferencing, and the first thing I would like to do is that the thing which we did earlier as well, starting with software, but I think we have seen it. So let's take another case. One of the cases which we discussed was how the model react to the words which generally ends a job title. So engineer is one of the word, or manager is one of the words which ends a job title. So if I give manager as a word to my language model, which we have trained already on the job titles, we can expect the model to end this, like to return a stop character saying that, hey, there shouldn't be any auto completion for this word because this is generally the end of a job title. So I have inferenced 20 samples and I can visualize these samples, and you can see in most of the cases the model is returning manager with an empty character saying that, hey, for manager there is nothing I can predict. Most of them were stop characters, that's why we ended at that point. And what prediction is just manager, no autocomplete. One time it has manager apprentice, but since it's a neural network and we don't have a very efficient architecture, or we don't have a very huge corpus of data set, it can happen. But you can see in most of the cases it is not auto completing it because the job titles are generally ending with a manager. I can do the same thing with engineer as well, and I'll probably get a similar thing here. And yeah, for engineer it's performing even better. It's not even auto completing any of the cases. Most of the 20 samples it's ending with an empty word. No autocomplete for engineer, but the words like software, the words like research, these kind of words, we think that this should be auto completed, and the model should give some efficient prediction. So I can see if I give software what the model auto completes with, and these are the autocomplete completion suggestion. The first one is software engineer, software analyst, software intern, software analyst, software engineer, software museum, that doesn't make sense, software supervisor, software engineer, software developer, again software financial doesn't make sense, software architect, software and recovery instructor, okay, software systems. You can think of like 70-75% of the auto completion is actually relevant, and maybe 10 to 20% is not that relevant. It can be due to the model architecture, the lack of information in the dataset, or the dataset being that small. A lot of things can be there for the machine learning model to not predict a lot of times, but you can you get the gist, you get the intuition that how an auto completion engine works, how you can build a language model that can autocomplete things for you. I can maybe practice with more words. Maybe I can practice with grade, and we saw that grade was followed by teacher a lot of times. So we can see what we get: grade smokehouse director, grade coach, grade teacher, grade machine operator, grade grooming, grade operator, grade analyst, grade flex. A lot of times grade is ended with a stop character. Grade traveler engineer. So yeah, this is like grade teacher is also coming up, which we saw in one of the job titles. So model is actually learning, and it is giving us with some good autocomplete suggestion. Now instead of that, I can also let the model go rogue maybe, or let them predict whatever they want freely. So I can probably give the stop character as the start word, and I can say the model that, hey, now I am giving you the um, liberty to predict some random job titles for me, and I can let the model predict maybe 20 job titles, and we can see what the model has predicted here. Okay, so the model predicted gasket squad, Copra entrance technician, Spanish physician, pre-press, drywall clerk, airplane cabin, longitudinal float installations, spare journalist, carpenter dean, client manager, wine launch analyst, induction placer, warehouse clerk, teacher asset protection associate, film concierge coordinator. So you can think multiple of this doesn't make sense, but a lot of job title will make sense as well. The problem is the model is not big, not trained on enough data set. So that is why when you will make it randomly generate job titles, it will not do that well. But if you want to use this model for autocomplete, then it will be able to do generatively or comparatively well, because at that point of time you are hand holding the model with some relevant starting point so that they can go ahead and make some some meaningful predictions. And that's what we want to do, and that's why the autocomplete works so well in the model which we have built. Now this is the end on this lecture. We build a language model from scratch. So if you have came this far, you should have a decent understanding how you can build a language model. Now the neural network architecture we used was a very basic architecture of multi-layer perceptron where we have some linear fully connected layer followed by a batch norm and a tanh activation. And it was able to with this actually with this architecture we were able to build a very decent autocomplete engine, which we show earlier. Now what can happen is that if I like get a huge data set much larger than what we have trained the model currently, and if I replace my simple architecture model with maybe a highly powerful transformer architecture, which is more complex and more powerful, we can maybe uh, generate a GPT model with enough compute power. And this is how it is a GPT model or any large language model is also trained. This is the basic concept, where what they do is that uh, the transformer architecture is the heart of these large language model on the model on which these LLMs are trained. We use a transformer architecture and we get a huge corpus of data, and we have an embedding. We decide the dimension of the embedding the way we decided here, and we let the transformer architecture model get trained on the huge corpus of the data which we pulled from the World Wide Web, and we let the embeddings learn the patterns and the relationships between the words coming up from the World Wide Web. And after training a huge on the huge corpus of data, we with the transformer architecture we are able to get decent embeddings which captures a lot of information, which we can further use to make these models perform some decent or informative autocomplete. And after that we can perform another series of fine tuning to make it a chat model. This is how it is done actually, and you now understand how you can what is the internals of training a language model and how you can build a language model of your own. Now what you can do is that you can experiment with this architecture. You can experiment with a lot of with this architecture a lot of different parameters as well. You can experiment with the number of iterations. You can experiment with the learning rate. You can experiment with the batch size. You can experiment with a lot of different things. Maybe you can experiment with a totally different data set, and you can yourself see what you can build and how useful predictions your language model is making. And yeah, this is what this session was all about. Now if you like this session, you can like this video, you can subscribe to the channel. This is the AI Engineering 101 playlist, where we are learning a lot of different concepts involved in the AI engineering and the machine learning domain from scratch. So if you find this useful, feel free to share the channel with others as well, and subscribe to it, and I'll meet with you in the next video.